Today's problem is find k smallest sum pairs. Difficulty medium. Accuracy, um, it's not real high. It's not real low. The thing that makes this problem difficult, I think, is something that may not occur to you at first, and it's something that's not really well explained, and there's no examples to illustrate it. So anyway, here's the problem. Given two integer arrays, array 1 and array 2, sorted in ascending order. Okay, see, that's actually not right. It doesn't show up in the examples here, but the test cases have duplicate numbers. Okay, so it's having duplicate numbers in an array is okay. So it's really sorted in non-descending order. So you get the two arrays and you get an integer, k. So your task is to find k pairs, and obviously if you get something like this in an interview, well, any kind of interview question, you want to be clear about whether or not your arrays can have duplicates. Does ascending really mean ascending, or does it just mean non-descending? So you've got the arrays, you've got the integer k. Your task is to find k pairs with the smallest sums such that one element of each pair belongs to array 1 and the other belongs to array 2. Return the list of these k pairs where each pair is represented as a list containing one element from array 1 and one from array 2. Note, you can return any possible k pairs with the smallest sums. And the driver code will print true if it's correct, and it will print false if it's not correct. All right, let's look at the constraints here. First, array 1 size, the size of the arrays will be between 1 and 50,000 inclusive. The elements in the arrays will be between 1 and a billion inclusive, and k will be between 1 and 1,000 inclusive. Time complexity, k log k, auxiliary space, k. Okay, so that's a hint that we don't want to just, well, actually, let's look at the topic tags as well. Priority queue, heap. It's a hint that we don't want to just load up a heap with these array integers. I mean, that's not going to help us anyway, because the arrays are already ordered. So putting the integers in a heap is not a help. But I mean, we're going to put something in a heap. Also, the fact that the auxiliary space is O of k is, again, we don't want to just, whatever we put in the heap, we don't want to just put everything in there. And actually what we are going to put in the heap is, we are going to put an integer array, and the integer arrays are going to consist of sums, okay, and indexes. Maybe this would be better with an example. Well, actually, let's look at one of these examples. The second example is probably too simple, but this example, we have two 3-element arrays, and so there are 9 possible combinations. Now, we could, enumerate the 9 possible combinations and find out which sums are the smallest. It doesn't seem very fruitful, because we're not taking advantage of the fact that we know that the smallest elements are in the front of the arrays. Also, it's an n-squared algorithm, and that's not what we want. So maybe we can't, yeah, let's do an example here. Let's use the first one as an example. And let me move this over here. I'm going to have to move this a little bit, so I want to be able to see the example and the code. Can we do that? Pretty close. Pretty close. The input here is, let me scoot it over. I'll scoot it back. The input to the or the method signature is 2 integer arrays as input and the integer k. All right. We're going to create a list of lists. This is going to hold our result. We're going to create a priority queue. It is going to keep track of, well, on the top of the heap will be the current smallest sum and indices of the numbers that we're using. The index into array 1 and the index into array 2. But as far as the ordering, the only ordering that's important is ascending by sum, which is the first element. We need a set. It's not going to be obvious from this example why we need a set, but I'll talk about that at the end. Now, we know that the smallest possible sum, because the arrays are non-descending, the smallest possible sum is to add the first element of array 1 and the first element of array 2, which is what we're doing here. And we're adding index pairs to a set. Again, the reason for that is not going to be obvious at first, and we'll discuss it at the end. All right, let's go up here so we can see the whole loop here. Now this set add, index comma index. Because we're using small arrays, the comma is not important. I mean, with larger numbers, it would be important, because if you had, even 2-digit indexes, you could have index 1 and index 11. Now, you can't just string those together as 1, 1, 1, because then you don't know if it's 1, 11 or 11, 1. But I'm not going to write commas as I'm doing this, because our numbers are not big enough to require that distinction. So, first thing is I need to put the heap somewhere, and I need to put the set somewhere, and I need to put the list somewhere. All right, the heap is going to go over here. So we're going to add the first element of each array, and that comes to 3. All right, 3. And the indices are 0 and 0. Now this is our heap. All right. What else? And adding to the set, 0, 0. Okay, the set, I'm going to put the set here. 0, 0. I'll give you a hint here. The set is to avoid using duplicate indices. Again, that's not, it's not clear from the explanation or the example. The way that I found out about it was to run the thing, and it failed, and I can see the reason it failed is the use of duplicate indices. I mean, it's obvious once you see it, but anyway. So let's see, result, add. So adding to the list will be array 1 at index 0, array 2 at index 0. I'm sorry, we should go up here and say min-heap poll. That is this item here. There's only one item on the heap right now. When that comes off, I is going to be 0 and j is going to be 0. Right? And now we can erase that. And we're going to add to result this list. Array 1 at I, array 1 at 0, array 2 at 0. So here's the first element in the list. 1, 2. Okay. Now, what is the next smallest sum? Well, there's two possibilities. The next smallest sum is either going to be obtained by keeping the same index in array 1 and advancing the index in array 2, or keeping the index in array 2 and advancing the index in array 1. We don't know which is which, but if we put them in the heap, that's going to do the work for us. And so that's what we're going to do. I plus 1 is 1. Is that greater than the length of the array 3? No, it isn't. So the string key is going to be 1, 0. Is that in the set? No. I'm going to jump ahead here to set add key and say, all right, well, we can add that then. 1, 0. And in the heap, we are going to put array 1 at 1, which is 7, plus array 2 at 0 is 2. That's 9. All right, so that goes in the heap. 9, 1, 0. Okay, go down here. How about j plus 1? J plus 1 is 1. We're fine on the length. The key will be 0, 1. Is that in the set? No. So let's add it to the set. 0, 1. And in the heap, we will put array 1 at 0, which is 1, and array 2 at 1, which is 4. So the sum there is 5. Indices are 0 and 1. Okay, back to the top of the loop. K is fine, min-heap is not empty. We will poll it. We will get this element, and temp 1 will stay at 1. Temp 2 will become 1. Right? So now we can poll that element. Result, add array 1 at 0, array 2 at 1. That would be 1, 4. Okay, so that goes in the list. Now we got to figure out what the next possible smallest sum could be, and we can get that either by advancing array 1 or either by advancing I or advancing j. So I plus 1 is 1. So the next smallest number could be 1, 1. What is 1, 1 would be 7 and 4. That's 11. Okay, so that goes in the heap. 11 and the indices 1 and 1. Actually, I didn't check to see if it's in the set, but it's not. 1, 1. Okay, what happens if we advance index j? J becomes 2. The key becomes 0, 2. Is that in the set? No. All right, well, put it in the set. 0, 2. And let's look at what can we put in the heap. 0, 2, so that would be 1 and 6 for a sum of 7. So that goes up here. 7, 0, 2. All right, back to the top of the loop. And we pull the heap, so that would be this element right here. I would become 0, j would become 2, and add to the list array 1 at 0, which is 1, array 2 at 2, which is 6. So the next element in the list is 1, 6. I just noticed we're doing a little extra work here, but so this comes off. All right, K is decremented. K is now 0 because we have all of the elements in the list that we want. We are going to push one more element here. In this case, J is too big. We are not going to push anything, and then we're going to drop out of the loop, and we're going to return 1, 2, 1, 4, 1, 2, 1, 4, 1, 6, which is can't see everything, but that is the correct answer. All right. What I wanted to talk about on the duplicate indexes is this. Let me erase this and just add another short example. Let me add a couple short arrays here. Here's array 1, 6, 6, 9. Array 2 will be 4, 5, 5. All right, as in the first example, first thing that we put on the heap is the sum of the first two numbers and their indices, which in this case is 10, 0, 0. We also add to the set 0, 0, the two indices that we used. Now, we can add a couple more numbers to the heap, and that would be the sums at 0, 0, 1, and 1, 0. All right. So the first first element comes off the heap, and then what we add is 0, 1, which is, oh, you know what? Here's what I forgot. In the process of doing that, we also added to the list a small sum, the smallest sum, 6, 4, right? Now, we will add 0, 1. Is that in the set? No. So we'll put it there, 0, 1. And we will put 11. 11, 0, 1. Now what about 1, 0? Is that in the set? No. So put that, 1, 0. 1, 0 is 6 and 4, so that's 10. 10. 1 and 0. Okay. So we're going to wind up putting another, because this is at the top of the heap. That's the next thing that's going to come off of there, and we're going to use the indexes 1 and 0. So we're going to have another 6 and 4. Okay, that's fine. That is fine. What's not fine is that as these come off the heap, we are going to have to generate a new possible smallest sum. So for 1, 0, the next possible smallest sums would be 1, 1 and 2, 0. Okay? this one, now if this comes off the heap, we would generate the next possible sums. But again, that would be 1, 1, and 0, 2. So the thing is, we've got to make sure that we don't add this a second time. It turns out, if you run the full test suite, that duplicate numbers are fine. Like what that is, it's this 6 and this 4, followed by this 6 and the same 4. That's fine. It's just that what we can't do is we can't put like the duplicate 1, 1, which would be this 6 and this 5, and then add another item to the list consisting of this 6 and this 5. So that's what the set is all about. Because in the process of doing this, there's a possibility of generating duplicate index pairs, and that is not allowed. So that is what the set is all about. All right. Having said all this, let's try and run this. Let me move this out of the way. Okay. Yeah, 1 out of 2. The first run was a learning experience. But I've shared with you everything that I learned from the first failure, which is, as I said, is that you have to handle the possibility of generating duplicate index pairs. So I hope that you will go ahead and like the video. You can subscribe to the channel, get notifications on new content, and we'll see you next time.